Okay, let's dive in. We're going to talk about a story that, well, every developer knows all too well. The roller coaster ride from a successful launch to a full-blown crisis, and the seriously elegant piece of tech that saves the day. All right, so picture this. You've been grinding away, day and night. You finally push that code, you deploy the feature, and boom, it's live. This is it, right? The moment of truth. And what do you know? It's a massive hit. The traffic just starts climbing and climbing. More and more users are flooding your site. They're loving the new feature. I mean, this is the dream scenario, isn't it? But then, things start to slow down. The site gets kind of laggy, unresponsive. Users start seeing errors pop up. And just like that, the dream is turning into a total nightmare. Why? Because your single, lonely server is just buckling under all that pressure. So here's the thing, this slide really gets to the core of the problem. With a single server architecture, every single user request hits the exact same machine. Think about it. Need to deploy an update? You got to restart the server, and that means downtime. Traffic suddenly spikes. It's going to crash. It's what we call a single point of failure. And you feel like you've hit a dead end. You've tried everything, right? You've optimized the code. You've beefed up the server with more memory, more processing power. That's called scaling up, by the way. But then you get the news. Get ready for 10 times the traffic. And you just realize you've hit a wall. There is absolutely no way one server can handle that. And right when you're about to have a full-on panic attack, a solution comes into view. And this is the key insight, really. Don't just try to make your one server stronger. Instead, add more servers and get smart about managing the traffic. And that's where the hero of our story comes in, the load balancer. And this image, it just illustrates the transformation perfectly. On the left, you see our old, fragile setup. And on the right, a whole fleet of servers all working together with a load balancer intelligently sending traffic where it needs to go. We've literally gone from a single point of failure to a resilient, scalable system. So, what exactly is a load balancer? Well, the best way to think about it is like a traffic cop for your application. Instead of users hitting your server directly, they first hit the load balancer. And it looks at all your available servers and says, okay, you go to this server, you go to that one, directing each request to a server that can actually handle it. So yeah, this traffic cop pretty much solves all those problems we just talked about. Let's break down exactly why it's such a game changer. Okay, first up, deployments become seamless. You can take one server offline, update it, and the load balancer just sends traffic to the others. Zero downtime. Simple as that. Next, you get way higher availability. If a server just dies, the load balancer automatically takes it out of rotation. Users never even notice. It also seriously enhances security by hiding your server's real IP addresses. And finally, it can even handle the heavy lifting of encryption, which frees up your servers to do what they do best, deliver better performance. Okay, so that's the why, right? It makes our system scalable, resilient, the whole shebang. But how does it actually work? Let's pop the hood and take a look. Right, and this is the magic question. I mean, for this whole thing to work, the load balancer has to be smart. It can't just be sending traffic to a server that's offline or struggling. So how does it know? How does it keep track of everything? Well, it does something called a health check. And you can see it here. It's constantly pinging each server at a set interval, like, say, every 30 seconds. If a server doesn't respond within a specific timeout period, it gets a strike. And after a certain threshold of failures, the load balancer just marks that server as unhealthy and stops sending any traffic its way, at least until it's back up and running again. Okay, so it knows which servers are healthy, but how does it decide which healthy server gets the next request? Well, the most common way is this beautifully simple algorithm called round robin. Now, sure, there are more complex strategies out there, like sending traffic to the server with the fewest active connections, but round robin, it's the classic, and it's super effective. And it works, well, exactly like it sounds. The first request comes in, it goes to server A. The second one, server B. Third one, you guessed it, server C. And once it hits the end of the list, it just loops right back to the beginning, back to server A. It's just a simple, fair, and really effective way to spread the load evenly. All right, so you might be thinking this all sounds super complicated to set up, but it's really not as bad as it sounds. It basically boils down to configuring just 3 main parts. Let's take a quick look at the blueprint.
First up, you have listeners. These just watch for incoming connections on a specific port, like port 80 for regular web traffic. Next, you set up your routing rules. These rules are pretty cool. They tell the listener where to send that traffic based on the request itself. For example, you could say any request for the admin page goes to a special group of secure servers. And speaking of which, those groups of servers are called target groups. They're the final destination for all that user traffic.
So, okay, we've solved our big crisis, we can handle massive traffic, and we can deploy updates without any downtime. But this awesome new architecture, it actually introduces a really fascinating new problem. So think about it. If a user logs in and that request hits server A, but their very next click gets routed by the load balancer to server B, how in the world does server B know they're logged in? Now that's a question for another time.